Also, we're going to record this, and yeah, just want to make sure you're all okay with this being recorded. It's not going to record any video with you all. It's mainly just provide this for people after the conference if people want to go back through the material and that sort of thing. They can. So, all right. With that, I'm going to go ahead and get started here. I know a couple of you are still waiting on the Jupyter Hub to spawn up. If you do have any questions, either Troy or someone can walk around and help you. Otherwise, ask other people at your table, or you can always raise your hand and ask me as well. So everyone should have by now logged in, and you should see this view on your web page. So today's workshop is running on the Pangeo binder. And for those of you who aren't familiar with Pangeo, it's an organization all focused on open science, open source software, with sort of opinion on Python is pretty great. So we thank them for providing the platform that we're running on today. And this platform already has our environment installed, so we're not going to have to install any individual packages. It's all ready to go. Also, this workshop material is available after. So if you want to go back through after this conference is over, you can always go back through these notebooks and try to go back and understand things a little bit more in depth. If you're having an issue with the notebooks, that links that I sent, this is what's called the Jupyter book. And this already has all the content pre-rendered. So if you don't necessarily want to go through and execute the content as we go, you can always look on here, and this has all the notebooks already loaded up, and you can just scroll through and follow along to what we're going through. You can always copy and paste these different sections following on the right. So this is a pre-rendered web page. Everything's visualized here, and you can always use this as well if you don't want to follow along within the binder, although using the binder is recommended just because you can change things and actually execute the code as you go. So today's workshop is basically going to be sectored into three main parts. We're going to talk about working with different types of meteorological data using the Python ecosystem. And specifically, we're going to work with radar data using PyArt. The next section is going to work with different other observations other than radar using ACT, which is the Atmospheric Data Community Toolkit. And the last section, we'll talk about some of the Pangeo related packages, which when you talk about the Pangeo stack, it's mainly X-ray, along with some really nice tools like DASC, which is used for parallel and distributed computing, as well as some of the interactive suite, like HVplot, so you can have nice interactive plots in addition to your usual static plots, and also Intake ESM, which is a tool to work with Earth system model data, especially like CMEP data, as well as other large experiments. So let's go ahead and get started. Let's get down to it. So you'll see a notebooks directory. And for those who aren't familiar with Jupyter Lab, is anyone here who has never seen Jupyter or Jupyter Lab? No? Okay, sweet, great. So this is Jupyter Lab. We're going to click on the notebooks directory, which will show us our different portions of the workshop. And we are interested in starting with PyArt. So we'll go ahead and click PyArt there. And you'll see a PyArt Basics as well as a PyArt Gridding notebook. Let's go ahead and start with PyArt Basics. So you're going to double click PyArt Basics, which will pull up in your main view here, the notebook that we'll go ahead and start with. People following along with that? Yes? All right. So within this notebook, we're going to cover in general overview of PyArt, which stands for the Python ARM Radiation Toolkit. And so ARM Radar Toolkit, I should say. And so this is a really great tool when working with radar data. It's also one of the packages that I help maintain. So definitely answer some questions and that sort of thing. So we'll go ahead and cover reading data using PyArt, which is sort of always the first step. An overview of what this object is that you actually load into your notebook, and then we'll go over some plotting techniques of the radar data. Also, at the top of this notebook, you'll see some prerequisites. So we're also tightly related to the Project Pythia project. And this is all about teaching people in the general geosciences and especially atmospheric sciences how to get started with Python. So if you follow some of these links, I'm going to use some Cartopy, which is a mapping library, matplotlib, which is a general data visualization library, and Numpy, which is for working with data. I'm going to talk about some of these different packages. Obviously, with a little under 2-hour workshop, I'm not going to be able to dive into the deep basics of all those fundamental tools. But if you click these links, this will take you to additional content if you want to go through after the workshop and really dig into some of these packages and how you can use it for your research or your classes and analysis. You can definitely dig through here. Project Pythia is a really great resource that you all can use. So with that, we'll go ahead and jump right in. So with Python, a lot of the time, your first step is importing all these really neat tools. So these are the different packages we're going to use here. We're going to use Cartopy for mapping, matplotlib for our data visualization, Numpy for working with some of those arrays, and then also PyArt, which has all those nice tools. So we're going to go ahead and run that first cell, and you'll see that block of text that tells you, hey, you're using PyArt. You should cite us if you use this package, which when you're working on a paper or even presentations and stuff, it's always great to cite the software. This is something that's really important within the ecosystem. So go ahead and cite that Journal of Open Source Research paper, or Journal of Open Source Research Software paper. So what is PyArt? So PyArt started about a little over 10 years ago. The whole project was focused around working with weather radars and sort of moving past proprietary software through the different vendors, moving to this open source model, which was all started by Scott Collis at Argonne National Lab. It's been supported by the Atmospheric Radiation Measurement User Facility. So this is a DOE program that does tons of atmospheric observations all over the world. And so fortunately, that program has continued to fund this software for the past decade. That's how I'm funded primarily. And so, yeah, the software is all on GitHub under the BSD license, which is basically an open source license. You can use it for whatever you want. And this can run on Linux, Windows, as well as Mac, which I'm running in this case. So what can PyArt do? So PyArt is, like I said, really great for radar data. So you can use it to read data, create plots of your data, correcting moments, mapping to a Cartesian grid, doing different sorts of retrievals, and then also writing out your data to whether it's gridded files or in the radial format, CF radial. So the data we're going to be using today, and it's used across the different examples, is from the SAIL field campaign. So this is the Surface Atmosphere Integrated Field Laboratory. It's out in Crested Butte, Colorado. This is a beautiful view of the radar that we're using as a part of this field campaign. And so, yeah, we'll be working with some radar data as well as some other measurements from this field campaign out in beautiful Crested Butte. And this is actually from yesterday, an animation for looking at the radar. You can see all the nice fall colors, and yeah, really cool area and a really neat field campaign that we're going to get some beautiful data from. So let's start with reading our data. So Python has this idea of modules, which are basically these parts of the package that include different toolkits. So for example, the IO module stands for input output, and this is where the read function is at. So if you're interested in all the different types of data that PyArt can read, I would suggest going to the PyArt.io documentation, which has a list of all the different read CF radial. You can read NextRad files. You can read all these obscure radar formats because everyone likes to have their own format. But we have this general IO read where it will try to guess what the format is. And this is often the easiest way of reading in your data. So if you add the question mark after that module, so it goes pyart.io, which is the IO module, and read question mark. This is actually a nice way of checking within your notebook what you can pass to this function. So I use this quite a bit. And so here we could see, all right, pyart.io.read takes in the file name and some additional keyword arguments. We don't need to worry about RSL. So basically we pass it a file name and it'll load it into our notebook. And you'll see that it returns here at the end a reader object, which is what we want to work with. So I already put some sample data in here. So this is the path to the file. It's within this data directory here. And if you go ahead and run that cell, you'll see that it returns this weird string that says pyart.core.radar.radar. So let's talk a bit about what this radar object is. So Python is what we call an object-oriented language. It's all based around this idea that we have these objects that we can store a lot of our data in. And in this case, we're storing radar data. So this radar object is where the actual data is at, as well as relevant metadata that allows us to work with our radar. So if we want to actually look to see what fields are present in here, we can do radar.fields.keys, and that will give you a nice list of what sort of data we have in this object. So you notice we have corrected velocity, corrected reflectivity, corrected differential reflectivity, corrected specific differential phase, and corrected differential phase. So that's always nice to be able to check kind of what fields we have in our data, in our radar object. So if we actually wanted to work with one of these fields, let's say we want to work with corrected reflectivity, if we actually look to see what's in this radar.fields object, this is what we call a dictionary. And this is what has all of our data. So you'll see that it has the long name, which is corrected reflectivity. It has our units. And then if we actually look at data, so we actually look at the data here, it's just a Numpy array. So this is the actual data for that given field. So if we want to look at type here, it's just a Numpy array, which is a way of representing data within Python. So if we want to check the size of this, so we can do the dot shape, that will tell us that it's 9,013 by 668. You might be wondering what do those numbers mean? And the dimensions of our data is the rays by the gates, which if you're not familiar with radar data, I was going to pull out a marker, but the virtual people can't see that. But basically the way that the radar works is it goes out along these different rays. And so it scans at different azimuths around. This is a PPI scan that we're working with, which I'll talk about more in a bit, but it goes out across different rays. And then the gates are basically how far from the radar those individual gates are at. And so this is how our array is structured. And if we wanted to look at one of these specific fields, so if we wanted to look at like the 300th ray at the second gate, go ahead and run there. So yeah, fortunately, when you're plotting it, you don't have to worry about any of this. You don't have to worry about the way that your data is shaped. You don't have to worry about feeding that directly into matplotlib. We have all these plotting utilities already in PyArt. So the most common one is this radar display, which whether it's a PPI, which is basically going across like a single elevation and basically giving you the horizontal view, or if you're working with an RHI, which is more of a cross section through your field, you can use these interchangeably, which is really nice. So radar display is one. Radar map display is really nice if you want to display it onto like a map with latitude and longitude. And then we also support airborne radar data. So if you wanted to display it onto an airborne plot, you could do that. Today, I'll be discussing radar display and radar map display, just because these are the most common displays you might want to work with. So let's go ahead and create our radar map display. So we'll first start by creating a figure. So this is plt.figure. And you'll notice that that doesn't really give you anything once you create that figure. But once we add in that display, you'll see that it still doesn't give you anything. So we set up our display first. So this display object, and then we use plot PPI map. So display.plot PPI map. We pass in which field we want to plot, and you'll see that it returns our field there, which, as I mentioned before, we're working with data in the mountains in Colorado. So we have a lot of beam blockage. This is real data, and this is the lowest elevation scan. So that's all right. It's not great by default. So let's take a look at some of these different parameters, or these different additional things we could pass into this plot PPI map to make this a little bit better and to make this a little bit more clear. So this plot PPI map takes in a few different arguments. So we can pass in which sweep we want to use. And so for those of you who aren't familiar with the radar data, the sweep is basically the number of the elevation. So the radar goes around, for example, ½ degree. So that's the first sweep. And then it might go up to like 1.5 degrees for the next sweep. So that's basically like which sweep it's going up and which elevation scan it's going up in this case for the PPI data. So we're going to tell it we want the 4th elevation scan. Since this is Python, it's zero-based indexing. So that's sweep 3. We can specify our Vmin and Vmax, which is basically the minimum value for our color bar, just to make that more standard. We're going to use this radar map display. So we want to specify our projection. We're going to use PyArt has some really nice colorblind friendly color maps, which I highly recommend using. A great one is this Homeyer rainbow. There's also a variety of other ones that you can check on our documentation. And then that plot above, that was Homeyer rainbow. It sort of has some defaults built in. So something just general research advice, use colorblind friendly maps. An example of a not colorblind friendly map is Jet. I would not recommend using Jet. But yeah, so we're going to use this Homeyer rainbow, which we put this PyArt underscore Homeyer rainbow, which gives us access to that color map. We can also specify our latitude and longitude lines. And yeah, now our plot function looks like this. So we're plotting corrected reflectivity. We're plotting the 4th sweep here. We're setting our minimum maximum for our color bar, and we're setting our color map. So we're going to run that, and that returns a little bit better than our last plot. So we have some nice latitude and longitude lines in here. We have the 4th sweep, which is at 6 degrees, which is a little bit higher up in the storm. And this is a snowstorm, by the way. This is from mid-March of this past year. And we can actually see some precipitation within our map. We have a nice color bar here that's colorblind friendly, and we're good to go. So there's a bunch of other parameters you could change here, which again, if you do your display.plot PPI map question mark, that will return all these different parameters that you can use. So if you want to turn off your color bar, you can do that. If you want to change your color map, do that. You can set some minimum longitude, maximum longitude, change your height and width. You can tune this however you want. So there's some really nice options here. So let's say we want to use a different color bar. So for example, I know within this department, carbon 42 is very popular. So we can plot it up, change the color map argument. We're still looking at corrected reflectivity, and we get our beautiful carbon 42 color map. Let's say we want to do a different elevation scan. So we were looking at the 4th elevation. Let's say we want to look at the 7th elevation. We could go ahead and do that as well, passing in a different sweep number. So yeah, there's a lot of different options. Yes.
This is related, but a little bit off. Is there a function within Fire that you can adapt a little bit more the color bar, like playing with the spacing between the graph? And I think that's my main issue that I've had with Fire, that I haven't, at least I haven't found more of a more flexible color bar that I can play around with the distancing or the title. I've only, at least on the Fire documentation, I've only seen specific functions of like turning it off or turning it on or changing the text, but I've never found any more I guess editable coding.
Yeah, so within Pirate, we sort of pass some of that off to matplotlib, where it takes some matplotlib tuning. I'll go ahead and include this within the chat at the end. We have one of the recent issues we're working on at ARM is these data analysis cookbooks. So for example, this is one for sale, and this is linked at the bottom of the notebook. But within here, we actually have an example notebook where we do some customization with the, let's see. Yeah, my recommendation, yeah, so like here, this is a code snippet where we're actually grabbing the color bar. If you do display.cbs, that stands for color bars, and then you can get it into a nice object that then you can customize. Here I'm changing some of the spacing, and that looks a little bit nicer. So yeah, I'll go ahead and put that, I'll go ahead and link that within the Slack. But yeah, so we have these different cookbooks. We're working on continuing to build up our example gallery. We also welcome contributions. So if that's even an example you want to add to PyArt, it is Hacktober Fest this month. So contributions are always welcome. So let's go ahead and go back to our notebook. And another comment, so this was talked about a little bit yesterday. So like so we were looking at PPIs, which is basically looking these different sweeps and that sort of thing, sort of looking horizontally. But if we want to look more at the verticals, so basically where the radar cuts basically a vertical cross section through a storm, that's an RHI, which is a range height indicator. So fortunately, PyArt has support for this. So I included a sample RHI file in there. So if we go ahead and you follow the same format, you read in your file using PyArt.io.read. We plot up our display, radar display. In this case, this is on QC data. So it's still in the original field name, which is DBZ, which is what they decided to use for reflectivity. And so we go ahead and plot that up. And you'll notice some beautiful cross sections through some of the snow bands here, only maybe a couple kilometers deep, 1 or 2 kilometers deep. And yeah, just beautiful data from some of the snow. So yeah, this is how it's sort of the same API here. And it's a similar way of plotting your RHI data. Now, let's say we just had PPIs. So let's say we just had our scans sort of horizontally, and we wanted to be able to get a similar type cross section through our radar. So you can do that using the pseudo RHI. So we have this pyart.util cross section PPI, which will actually create one of these through the different elevation scans. So it'll go ahead and you feed it some given azimuth. So here we were looking at, this is 328 degrees. So starting at the top of the radar, that's 0 degrees, going around clockwise, coming all the way back around. I was at 328 degrees. So let's load back in our PPI. We use this cross section PPI at 328 degrees. and we get that. So this is really nice to use, especially with next ride data, which doesn't necessarily do RHIs. You can sort of create these synthetic RHIs through your storm and be able to look at this. This is also an illustration of how awesome RHIs are, just because you can see a lot more of that vertical structure. If you compare this from the PPI, the RHI, look how much how much more you can see within some of those snowbands. So yeah, this is sort of the basics of PyArt. At this point, I'm going to go ahead and jump into gridding. So PyArt, the gridding functionality is definitely one of the more popular functionality components within PyArt. And so within this notebook, I'll go ahead and go over like why gridding is important, how to choose a gridding routine, and then also grid up some data. So radar data by default comes in this polar/antenna coordinate system, this radial format. Or like I was saying before, the dimensions of your data are basically azimuth and range, where it's going around the radar, and it's also like the distance from the radar are the main two coordinates, which is great when you're working in this radial space. But if you want to transform it, if you want to compare to the same model data, model data doesn't come in these radial coordinates. So one of the common workflow pieces is actually gridding your data, taking it from these radial coordinates and converting it to some Cartesian grid, which basically Cartesian grid being your lat, long, and then distance above the surface. So this is really important when you want to compare to, for example, model data. So say you were running the weather research or forecasting model over some case, you might want to compare your actual radar observations to your model. So some questions when you're gridding radar data is, what should my resolution be? So thinking about how coarse or how fine of resolution. So say, should my grid be 500 meters apart or should it be like 2 kilometers apart? So taking that into consideration, which interpolation routine to use. There's a bunch of different interpolation routines out there, and how smooth should my data be. So let's load back in our PPI here. Why is that saying? There is a bug. So yeah, the sample sale PPI. It is a bug. I'll fix that. Yeah, so go ahead and change your string for the file path to sale or sample sale PPI. So yeah, so we load in our data, and then it's going to visualize it. This is the same data set we're looking at before. And you'll see it's in this native coordinate. So it's in the distance from the radar, and it's basically extending outward from the radar. So let's go ahead and grid this up. So basically the object we're going to convert it into is what we call a grid. This grid object has similar characteristics to our radar object, except it focuses more on actually being in an X, Y, and Z space. So yeah, let's go ahead, and the function to actually do the gridding is this PyArt map grid from radars. And so this is what we're actually going to feed our radar object into to perform this gridding. So before gridding, we're going to need to make some decisions. So we're going to have to decide our grid extents, so how big of a grid we want to use. If we go back to this plot, you'll see that our domain is mainly 20 or so kilometers east and west is where we actually have this precipitation, as well as roughly 20, maybe a little bit more than 20 kilometers north and south. So actually visualizing your data and digging into what sort of domain you actually want to plot it into is usually a good first step. So since we're roughly 20 kilometers north and south and 20 kilometers east and west, we'll use that as our domain. 15 kilometers might be a little bit overkill because we were looking at some of our precipitation. And it looked like it was only extending maybe a kilometer or two above the surface, but we'll just do that anyway. And then since this is pretty fine scale resolution, we can go ahead and grid to a 500 meter grid space. So I included some helpful functions here so we can set up our Z grid limits, which is basically the vertical direction, our Y grid limits going east and west, going north south, and then our X grid limits, which is going east west. So we set up our grid limits, we set up our grid resolution. We have this helper function to calculate the number of points. And we count the number of points in the Z direction. So that's saying that there's going to be 20 points going from 500 to 15 kilometers at a 500 meter space. And we do that for X and Y as well. And you'll see that we end up with a, that is AGR. Yep. So that's above, that's like the height above the radar. So we'll go ahead and run this grid from radars. So you'll see that we feed in our radar object, we feed in the grid shape that we calculated above, and then we pass in our grid limits, which results in this grid object. So now we can go ahead and feed that into the grid map display, which will return our gridded field. So being at 500 meter resolution, you'll notice that this is a little bit coarser than the radial data we were looking at before, but it is uniform, which is nice. And if you wanted to go through and actually change this to say 250 meter resolution, you could definitely do that. So if we went ahead and let's say we want to do grid resolution, if we want to do say 250 meters, we could change that, recompute the points. You'll see it now goes up to 58 instead of 29. You'll see that we have a lot more X and Y points, basically double. And if we go ahead and grid that again, you'll see that it takes a little bit more time since we're doing a lot more points within our grid. It's ready. If we look at that now, you'll see that's even a higher spatial resolution than we were looking at before. So actually applying this gridding routine, taking a look at your data and seeing what you're seeing within the gridded fields is always a good first look, and just seeing if what you're looking at makes sense. You also notice that I put in level is equal to 0. So this is basically saying the lowest level within our grid, which in this case is 500 meters. So we also have a nice utility here to plot a latitude as well as longitude slice. So let's say instead of viewing the horizontal, viewing across your latitude, longitude, you actually want to take a slice through this field. So we can use this plot latitude slice, passing in the desired latitude, which 38.91 looks about right. We're going to try to take a cross section right through here. So going right across there. So if we do that, you'll notice that we get this visualization, which is basically a cross section through our grid, sort of like an RHI, where we can see the vertical structure of our radar field. So you'll see some of those snow bands, again, extending a couple, maybe 3 kilometers up through the domain. You'll also notice our cone there. So that's where we don't have any radar scans because it's too high above the radar, and our elevation scans didn't go up high enough to actually measure that. So again, some helpful functions for taking a look at your data, investigating it, and getting into a little bit easier format to work with. Something that I don't know if a ton of people know is you can actually take this grid, and if you're more familiar with X-ray, which I'll cover a little bit more in a bit, you can actually feed it into an X-ray object. But then you can do your typical X-ray stuff, like selecting a Z value if you want to use, like, I don't know, 1500 meters. You can do that. Which again, I'll cover this more in a bit. But then you get it in that more easy to work with X-ray object that then you can play around with. Or if you want to do like the cross section, that's how you do that. So there you go. So in general, this gridding makes it a little bit easier to work with the radar data. You can get it into this X-ray object, and really the main use case is when you want to actually compare with model data, or if you wanted to say feed some sort of reflectivity field or some sort of velocity field or whatever from your radar actually into models and that sort of thing. This is a good way of getting it onto a more uniform and Cartesian grid. So, all right, and with that, I just want to highlight some resources if you're interested in learning more about PyArt. So definitely check out our documentation page. So if you go to what's that link? Fix that. So if you go to, or if you just search PyArt and go to our main documentation page here, we have a user guide here that kind of walks through installing, set up an environment. So especially if you want to actually install Anaconda and that sort of thing after the workshop on your own machine, there's some great documentation on that. How to become a contributor. Again, it's Hacktoberfest, which you can get a free t-shirt if you make some contributions. Super exciting. This is a good place to go if you're interested in some of the modules and that sort of thing, and some of the functionality, like I was mentioning, the IO modules. It's a good place to check out. Probably the most common place that I'll point new people to this functionality is our example gallery, which sort of has these the sample code in there with you, and you can look on here and say, for example, I wanted to look at a composite reflectivity. This is some new functionality submitted by Randy Chase. So let's say, for example, especially in the mountains, I wanted to look at composite reflectivity. You could take a look at this example. It has this nice copy and paste. You put in your radar, and you can go ahead and use this within your code and get similar figures. So this is really nice if you want to go on here and take a look at some of these examples, whether it's working with Nextrad data, plotting to a Cartesian grid. You can actually do some comparisons, looking at two radars and grid them on the same object, do some cool histograms. There's lots of cool examples here, which I would highly recommend using and checking out. This is sort of a good first place to start. We also have the notebook gallery. But yeah, so with that, I'm going to go ahead and jump right into another one of our packages we use quite a bit, which is called ACT. It might be something it's not as well known as PyArt, but it's still super useful when you're working with atmospheric observations. So ACT stands for the Atmospheric Data Community Toolkit. Again, this is supported by the ARM program here, which thank you, ARM, for supporting this development. It's open source. It's on GitHub. We have quite a few contributors to this package. And it's actually used within our QC process at ARM to work through all of our different field campaign data, develop quick looks and that sort of thing. And the way I think about it is basically any atmospheric observations other than radars. This is made to work with mainly non-radar data. So if you're interested in installing this on your own, it's called ACT Atmos. So you pip install ACT Atmos. This is already installed in this machine, so you don't have to install it yourself. And then also, so I didn't go over this, but go back to notebooks, click on ACT, and go into ACT Basics. This is notebook. So we're going to go ahead and do our imports here. So we're going to import ACT. That's our Atmospheric Data Community Toolkit. Similar matplotlib. We're also going to grab Bob. Don't use it too much, but yeah. So a common first part of the scientific analysis workflow is actually accessing data, which within ACT, we have this nice discovery functionality where you can actually download data directly from the ARM program using this API. So this allows you to search as well as download data from the ARM program. So for this workshop, I've already provided this sample username and token. So that's what we're going to be using here. And this is some data from the Southern Great Plains site, which I think there's one talk yesterday that was using some data from that site. If you're not familiar with the Southern Great Plains site, it's located in northern Oklahoma. There's some long-term climate. It's a long-term climate observatory there, which does a lot of great things for the community. So we're going to download some data, this FRSR data, and running that will return a list of files, which if we actually run our results here, that's going to give you a path to your data. So this is the data set we're going to be working with. So congratulations, you just downloaded a file from your notebook. Yay, we have data. Next up is to read this file into an X-ray object. So the difference between ACT and PyArt is that this main object that we use in ACT is actually an X-ray data set. Maybe a couple additional attributes added to it, but it's really just an X-ray data set. So this ACT IO, we're gonna read in this read netcdf, which returns this data set, which has all these different sorts of variables. So you'll notice we have like 150 variables here. So tons of different fields that we can work with and analyze. So it also has some nice CF functionality. So we can run this clean.cleanup, and that will go ahead and apply the CF standards to our data, make that a little bit easier to work with. And for those of you who aren't familiar with the CF standards, it stands for the Climate and Forecast Standards, which is basically the idea of using similar terminology for our different variables and metadata and that sort of thing. So now we have this X-ray data set that we can go ahead and look at. So we're going to look at this diffuse HEMIS narrowband filter. It's one of the variables within the data set. So we plot that up and we can see our radiation data there. So that quick thing that was saying that there's an error, I'm going to go ahead and go to my file and go to So go to your settings and unclick autosave. So that'll prevent that error from popping up. Yeah, ignore that. That's basically just saying that like we've downloaded data and our disk space is getting pretty big. And when we try to save this, we're running out of space. So if you go to settings and autosave documents, make sure that's unchecked. All right, so now we can see our radiation data. So this is in watts per meter squared. We can see our narrowband filter 4. And then the other nice thing within ACT, so we set up our display similar to PyArt. So we create a display object. We add our diffuse variable there. We plot up. ACT has this display object has a really nice functionality where it adds in this day-night background, where it tells you when it's night and daytime, looking at the latitude and that sort of thing, which is really nice when you're working with observations to know when it's night and when it's day. And then we also have this QC flag. So this is actually using within the different ARM files. This has already been QC'd, and this has quality control where you can see when we have bad data indicated here in the red and when our data is good indicated in the green. So when you're working with observational data sets, always a good idea to at least take a look at the QC flags and tell whether or not your data is actually good during that time so that you're not making any assumptions using bad data. So let's go ahead and filter some data. So we have this QC filter that we can apply to our data. We can add some tests there, and then we're going to delete the QC variable. We can again plot it up using this time series display, plot up our data, add the day-night background, and then use this new QC flag, which you can see there. So sometimes you'll have some instrument-specific QC tests. So for example, ACT has this fast Fourier transform test to detect shading. This is from this paper right here. So if we go ahead and click there, you'll see that it takes you to the functionality here. So if you're interested in more of what this FFT is actually doing, you can definitely read more there, and that has a link to the DOI as well. if you want to read more about that paper and how this is actually implemented. But in this case, I'm just going to apply this FFT shading test to our data set. Again, we follow that similar format of setting up time series display, plotting our data, adding that day-night background, and you'll notice that it applied that additional filtering. You'll also notice that this QC variable that we added using that FFT is now added as an additional line on there to QC. So again, this is super helpful when you're working, especially with field campaign data and some of these atmospheric observations, and need to apply this QC processing. And like I mentioned before, this is used quite a bit within the ARM program for our data quality, data assurance tests, and it's part of our operations. So yeah, so that was a bit about how to use the ARM Live API to actually go through and look at data. We applied some QC to our analysis and also plotted that up. So let's look at some of the other things. So the second act. So we're going to look at some of the other plotting utilities, working with some of the other data here. So a common part of ACT that people use is our windroses. So you actually can create these windrows plots when looking at wind fields. So in this case, we're going to load, this is another data set from the Southern Great Plains site. This is a meteorology data set. And B1 is the level of correction. So this has already been corrected, which is really nice. We're going to look at data from May 1st to May 31st of 2021. So we're going to load in our data using the ACT Discovery download data module. We're going to read in those net CDFs, get that into our data set. We're going to plot up our windrows here using the windrows display module. So with the windrows plot requires both the wind direction. So this is the wind direction WDIR, as well as the wind speed WSPD. We can set up our bins here, and we can add our legend as well. So running this, you'll see that it's downloading the data. So it's downloading a full day worth of data from the Southern Great Plains site. Actually, that's a full month of data. Sorry. That's from, yeah, May 1st to May 31st. So this is loading in a whole month of data from the Southern Great Plains site. So once it loads that in, we get a nice plot like that. So if you're working with windroses, again, ACT has some really nice functionality for this. And you can see looking here that we had 2% of the time it was calm. Quite a few cases where it was from the southeast, and especially some of those higher wind speeds indicated there. So generally southeasterly flow with some northeasterly component as well. So yeah, so this is a really nice function when you're working with some of that meteorology data. We also have some utility for working with the present weather. So if you want to actually decode some of the present weather, so if I actually look at one of these, so ds dot let's look at one of these. So these are all integers for the present weather codes. So we also have functionality that'll take and decode this and actually put it into something that's meaningful. So here we are checking for where it's not 0, because 0 means it's missing. You'll notice that we're able to decode those different codes. So there's sometimes when it's rain, not freezing, drizzle, not freezing, and so on. So if you're working with some of those present weather codes, it could be another helpful functionality. The ACT also has some really nice modules for working with Doppler LiDAR. So if you're working with LiDAR, we have some really nice functionality. For example, this ACT retrievals compute winds from PPI. So you can actually compute winds from some of the LiDAR data here. So we're going to read in some more ARM files. We're going to load in our wind data set, our LiDAR data set, and then plot that up. So we we load in our data set, we apply this compute winds from PPI to actually compute the winds from the LiDAR data. We load it into our time series display, add some barbs onto there, constrained time, and you'll see that this is derived from the LiDAR data. So there's some really nice retrieval modules. And yeah, if you're interested in that, go ahead and click these links in here. And this provides some additional information about how these were retrieved, as well as the actual paper. So if you're using this actually in the research, and this goes for PyArt stuff as well, always make sure to cite the paper that these retrievals come from, and make sure to check out some of these papers if you want to find out more about the technical aspects and how these algorithms are actually written and how they were originally implemented. ACT also has some functionality for working with SKUTs. So similar to the time series display we've been mainly working with so far, we have a SKUT display, which makes use of PyArt or of MetPy to set that all up for you. So in a similar fashion, we're going to read in some sample sound, set up our SKUT. We use our plot UNV, the UN, VUN, and so on. So within a few lines, you can create your SKUT here. And then if you actually wanted to display where your radiosonde path is, you can use this geographic plot display. You feed it the data field, which in this case is pressure. That's what we're plotting here. And then this will go ahead and grab the latitude and longitude, as well as whatever that third data field you want to plot. And you can see our sounding going across the Southern Great Plains site in northern Oklahoma, across different pressure levels. So again, if you're working with atmospheric observations other than radar, there's a lot of super helpful functionality here. In this last case, we're going to go ahead. We have a calculate PBL, so the planetary boundary layer height. We have a retrieval method for that from this Lewin Lang paper. So you just feed in your sounding data set, and that will go ahead and calculate your PBL height. So I know this was a lot of different things, and I'd highly recommend going back through this notebook and looking through the ACT documentation to learn a little bit more about all the different functionality it has. But again, when you're working with atmospheric observations, it can be a really helpful toolkit, both in terms of accessing data as well as visualizing data for your use case. So let's take a look at some data from SAIL. So SAIL is not the only field campaign going on in Crested Butte right now. There's also SPLASH, which is the NOAA field campaign going on there. So we're working with some NOAA collaborators on actually adding some discovery modules for some of their PSL data. So this is actually some little bit of radar data here. This is basically time height. And then we also are going to look at the parsable data. So we're going to go ahead and load in data from 22 UTC on this. This is August 1st of this year. So we're looking at 22 and 23 UTC. We load in, we have this module for accessing the sort of radar data. And then we're also going to read in the parsable data here, which that you can actually load in remotely. So you just feed the remote path, and you'll see that it downloads different moments. So debugging. Let's see where we went wrong. So you notice within the path here, you'll see that we have data. 22 UTC. All right. So for those of you who aren't familiar with debugging in Python, this is sort of a good quick use case. So you'll see here that it returned an error that my file name was wrong, which especially when you're working with data, you might run into this error. So yeah, I basically went through, and you'll notice that this is one file, this is another file. basically just had to pass in those new variables to this. So again, I'll post the corrected notebooks after the workshop. But yeah, so now that error is gone and we can work with our data. So we set up our time series display. We add our uncalibrated reflectivity here. You also notice that ACT has these colorblind friendly color maps implemented in there. So we can add those in. We're going to plot the reflectivity from the radar, and then we're also going to plot the number density drops from the parsable. So we go ahead and run that, and you'll see we have this nice time height where you can see our snowband, or this is during the summer, so these are actually rain bands. And then you can also see the number droplets down there. So yeah, like I said, ACT has lots of great functionality when working with atmospheric science data. So I would recommend checking out the ACT example gallery here linked at the bottom. So this has a bunch of different examples. For example, if you want to do like a multi-plot across different meteorological data, you can do that. You can do some spatial contouring, look at different QCing and that sort of thing. Similar to the PyArt gallery, there's tons of examples on here, which you can use for your different use cases. And then I also linked here. This is the SAIL cookbook that we've been working on. So this is an open science cookbook to work with data from this field campaign. And we're actually doing some precipitation estimation from radar. And there's all these different notebooks you can go through and check out sort of how we're doing this. This will be a radar product published by ARM over the next few months or so. But if you're actually interested in how we're getting this work done and how we're using these toolkits to be able to do this, it's really great to check this out and see if you can use this for your own research and that sort of thing. All right, so I will go ahead and pivot to our next topic. First off, are there any questions about ACT or PyArt so far? No? All right. So we're going to go ahead and pivot to more of the Pangeo related packages. The Pangeo ecosystem mainly focuses this idea of working around a common data model, which is X-ray. So is there anyone here who hasn't worked with X-ray before? Who has not worked with X-ray? Handful? All right. So yeah, so let's go over an introduction to X-ray. And even if you have worked with X-ray, there might be some things that you didn't know you could do, or some functionality that you might want to use. So for those of you who aren't familiar with X-ray, X-ray is the go-to package when working with gridded labeled data with X-ray. The whole idea of X-ray is the idea of labeled dimensions. So instead of having to know that your data is like, for example, time lat long, and instead of having to create your own indexes for that, X-ray makes it easy to do like dot select, latitude equals this, longitude equals this, time is equal to something else. It makes it really nice to work with this labeled data, which is so common within the atmospheric science and more general geoscience community. So within this tutorial, I'm going to cover how to create a data array, which is the sort of core object in X-ray. I'm going to go about the difference between a data array and a data set. We're going to go through how to subset, slice, and interpolate data, opening data with X-ray, and then some plotting with X-ray. And this morning, I actually added a little bit on some of the interactive plots that you might want to use. And that's another thing within the Pangeo ecosystem, is taking a look at using some of these high-level plotting packages, for example, HVplot, which we're going to be using, which instead of working directly with the JavaScript and that sort of thing, you can create these really nice plots that use your X-ray data set to intelligently read things and create a nice dashboard for you that you can use for your exploratory analysis or sort of your final research product. So as with the other cases, there's tons of material here that you might want to look into. These prerequisites include Numpy, pandas, which is actually how the indexing is working underneath. Date time is a really helpful module to understand kind of how date times work, as well as NetCDF, which is always something, if you're not familiar with NetCDF is sort of the go-to file format in the weather and climate sciences. And so all this is on the Project Pythia site. So again, if you click those, we have some really nice material that you can go through and understand exactly what NetCDF is and why it's useful, especially with metadata. So let's jump right in. So we're going to import some date time functionality. We're going to import NumPy, pandas, and Xarray. And then these last few packages I added in last night / this morning, which is more of the interactive plots. So we're going to import something to help with the date time ticks. Within Bokeh, we're going to add in HV plot, which is, like I was saying before, a high level package to work with these interactive plots, and then hollow views here as well. And we're telling it that we want to use Bokeh, but you could also, if you want to use, say, matplotlib, you could choose that extension as well. So, but in this case, we're using. So, introduction to data array and a data set. So, Xarray expands upon NumPy, where NumPy is great. Like, it has tons of great functionality, it's fast, and it has some really great functions, but it doesn't enable you to do some of the labeled indexing. It requires you to know like what number you're looking into in an array. It requires you to know exactly the order of your dimensions, and that's where Xarray comes in. So Xarray is basically building on the NetCDF file and basically trying to mimic NetCDF in Python. So it's basically going on that idea of having labeled dimensions and being able to work with your data using these common standards. So we're going to start first with creating a data array, which is sort of the basic functionality. This is the core sort of data component within Xarray. So it needs two pieces. It basically provides two pieces of functionality. So like I said before, coordinate names and values, which makes slicing and indexing a lot easier. And then also has these built-in containers for attributes, which basically, yeah, like say your temperatures in degrees Celsius or something like that. That actually keeps it in the objects. That way, you know, when you're plotting, it'll automatically add that onto your plot and you know what sort of units you're working with. So we're going to start first with creating a NumPy array. So this is creating a NumPy array, a bunch of random numbers, kind of around that 288 range. So we have this NumPy array. This is just an array of numbers. And so if we feed this into Xarray, if we feed just this NumPy array into Xarray, xr.data array, pass in our data, it's going to try to take a guess. It's going to set up by default. It'll set up the dim0, dim1, and dim2 with our data. But that's not super useful because what's dim0 or what's dim2? Like that's not that's not a big step forward. So we're going to want to actually add some information about what these dimensions are. So for example, is dim0 time? Is it latitude? What is that? So let's go ahead and add some dimension names here. So again, this is where the power of Xarray comes in, is adding these name dimensions. So we're going to create some more useful names. So let's set up, we'll feed in our data array, but instead pass in. So we know that we have 3 dimensions. We're going to set this up as time, lat, and long. So when we run this, you'll see that that's maybe a little bit more useful now. So now we have our dimensions time, latitude, and longitude, which is something that's very common within the atmospheric and climate sciences. So this is improved But the problem is that we don't necessarily know what time values we have in there. We don't know what latitude values we have in there. Those are just the dimension names. So let's create some space and time coordinates. So we're going to use pandas here to create a date time set of data. So we use this date range, which is going to create basically starting on January 1st, 2018. It's going to go daily by default, and we're going to create 5 days worth of data. Which again, the reason for this is if we look at our data shape, our time dimension has five values. So we're going to create this basically sample data array for time, where this is now a date time index. These are times from January 1st to January 5th of 2018. In a similar fashion, we're going to create some latitude and longitude data. So let's say we want to go from -120 to -60 with 4 points in between. And then if we want to go from 25 to 55 with 3 points in between. So we run that. That creates our sample data. So now if we actually look at these, you'll see that we have our longitude data, 4 values there. We have our latitude data with 3 values, and we're good to go. We have some coordinate information. Let's go back to our data array. So now we have our data, which is the 3-dimensional Numpy array. We have our coordinates. This coords is actually where we pass in the array of coordinates. So we have our times, which again is coming from up here, the state time index. We have our lats and we have our longs, and we also have our dimensions, time, lat, and long. So now this is something that's a little bit more useful. So you'll see that we have our array of values. So these are actual data values. We have our dimensions, time, lat, and long. But now at the bottom, you'll also see we have these coordinates. So now we have our time array, we have our latitude array, and we have our longitude array. So this is something that's a little bit more useful. The last thing we need to add is some attributes. So we take our data array, .adders, which stands for attributes. We'll add some units. This is in Kelvin, since that's around Kelvin, that's 280. We're going to add a standard name, air temperature, that's sort of conforming with the CF standards. And now, not only do we have the data, we have our dimensions, time, lat, and long, but now we have some attributes. So now we have our units and our air temperature. So attributes are not preserved by default. So something you'll notice that when you say, for example, if you wanted to convert from Kelvin to Celsius, if we apply this operation by subtracting 273.15, which is the conversion there, you'll see by default X-array doesn't basically drops the attributes there, which that's something to keep in mind whenever you're operating on these data arrays. It's going to drop those attributes. So in this case, like let's say after this conversion, we might want to actually add those attributes back in. So our new attributes would be like bag C. And then we might want to grab the same one from before, this air temperature. So if you're interested in learning more why X-array doesn't hold on to those attributes, you can definitely read it there. But in this case, it makes sense that it didn't hold on to the attributes, because otherwise, if you apply this conversion and it kept those units in, those would actually be wrong units. All right, so that was the data array. So a good way of thinking about the data array is that's like a single variable. So we were looking at air temperature there. A data set is basically a container for these data arrays. So you can think of a data set as basically a collection of data arrays. So your data set might include temperature, humidity, U and V winds, or something like that. And it contains a lot more than just those couple of variables. So let's go ahead and add some pressure data. So we're going to start around 1,000, add some random numbers, and you'll see that we end up with our pressure array. So in a similar fashion, if our data array, add some units, hectopascals, we had our standard name, and now we have a pressure array. So sweet, we have our new data array, and it has time lat ln, units, and so on. At this point, we can take our temperature array and our pressure data array, combine those together using this XR data set. And now we have an X-ray data set that has both temperature and pressure. It has those shared coordinates. And if you actually look at these different variables, you'll see that the attributes for those individual arrays is in there as well. So this is most of the time when you read in data, this is most of the time what you're going to be interacting with is this actual data set, which includes a collection of different variables. So this data set is aware that both these data arrays are on the same coordinate, which makes it super easy and helps them share some of that information. So if you want to actually access these data variables, you use the dot notation. So you can do ds.pressure, or if you want to use temperature instead, that's kind of how you would access some of those individual data arrays. Or you can use it in the dictionary sense, where you pass in the name of the variable in a string like that. So you can use either one, or sort of up to you, what's your preferred method of accessing those. That's kind of how you do that. So if you actually want to index your data, so you can do it the good old Numpy way. So if you know that you want the first number in a data set, or this is the second time within your data set, you can do that. That's not super useful, just because that requires prior knowledge that your time latitude is first, that you want the second value. You don't know what that time variable is, but you just want the second value. That's not super useful. And that's where I would recommend using the cell sort of API. So cell stands for selection. So let's say we wanted to select the second day. Let's say we want to look at January 2nd. So we use cell. So our temperature dot cell, we pass in our time array or our time string there. And that's, at least to me, a lot easier to work with rather than having to know the numbers of indices and that sort of thing. So we got the same result, but we didn't have to know anything about how the data array was created or stored. Our code is agnostic. So if we wanted to, say we worked with another data set that started on the second day and went for another 5 days out, we don't have to know about that difference in index. It works across those different cases. And code readability, like if you were to share your notebook with someone, this is a lot easier to understand. We're saying, hey, we're taking the temperature, selecting a single time, and that's a little bit easier and cleaner to understand. So one of the nice things within Xarray is it has sort of some default nearest neighbor sampling. So say within our data that we want to grab the 7th day, we don't know if that's actually in the array, but it's going to grab the nearest. So it's basically saying that, hey, we would like this day, but if that day doesn't exist within our data set, go ahead and grab the closest value to that. And then we could set like some sort of tolerance. In this case, 2 days is our tolerance. But yeah, so this is really nice. So for example, if you're working with some like gridded data and you want to grab like the vertical level or something like that, let's say you want to grab like 5 kilometers or something like that, or latitude, if you want to grab the like 37.3 or something like that, using this method equals nearest is going to allow you to grab the nearest and not necessarily know the exact data value of your coordinates, which is really nice. You can also do some interpolation. So this .interp method is going to actually interpolate your data onto some given coordinates, which can be nice. And that's all using SciPy underneath. You can slice along coordinates. So the slice notion here is basically I want to grab from the 1st through the 3rd across these longitudes and these latitudes. So that enables you to go ahead and grab that slice across your data. And then the other selection method is loc, which is a little bit faster. You can definitely look into that if you want to. Yeah, in the interest of time, I'll keep going along here. So that's going to actually open up some some net CDF data. So we're going to load in some. So ARM has a vertically pointing Ka band radar. It's called Kaiser, which has some absolutely gorgeous data. And this is from the SAIL field campaign as well. So we'll load in this. We'll notice that we have our time and range as our main coordinates here. So basically that time height. We have temperature, reflectivity, and mean Doppler velocity. And again, this was using XR open data set. You basically pass it that CDF file. So you'll notice upon opening this data set, we're able to take a look at our data here. We can see what variables we have in this data set. We can look at the attributes and actually see how this data was processed, what version, data streams, where it was collected. You can see the SAIL field campaign near Crested Butte, the antenna altitude. All this really neat information about our data set is all accessible within this X-ray data set. So similar to the dot, using like dot variable syntax, we can go ahead and look at the reflectivity field here. So this is reflectivity. It's the equivalent reflectivity factor units of dBz. And then you can see some additional information here. So let's go ahead and grab the first hour. So we're gonna use that slice syntax that I mentioned before. We're gonna grab from 0 to, in this case, we're going and grabbing through 5 Z. So if we go ahead and look at this, you'll see that we have all the way up through 4Z because our data set only goes up through the first 4 hours. So if we go ahead and look at this, you'll see that we have a similar data set here. We can do X-ray has some really nice functionality for calculating, say, mean or standard deviation. So you take your data field, apply the dot, in this case STD, but if you want to do like say mean or something like that, you can do those sorts of operations directly on your data, specifying which dimension you want to average across or apply some sort of operation. So let's go ahead and we're going to subset the lowest 5,000 meters. So we're going to grab a slice from 0 to 5,000 meters. And then we're going to grab the average across time. So you'll see here, we access our temperature data. We're going to grab the lowest 5 kilometers. We're going to take the average across time. You notice that we end up with this profile of temperature across our array. So X-ray has some nice built-in plotting functionality. So if we just call our new data array, this prof variable, if we just call .plot, let's load this again. Let's see. Let's try to run that. Yeah. So I'm going to go ahead and dig into, I don't know why. Let's go ahead and go into the interactive plots. So I'm going to talk a little bit about, especially since we're close on time, I'm going to go through the interactive plots. If you want to go back through and go through the matplotlib stuff at later time, you can. So I'm going to go through the interactive. So that's something I'd highly recommend within your research and that sort of thing, is considering making these interactive plots, just because typically your first step is sort of going through and looping through and creating like thousands of static matplotlib plots, which can be useful. And especially when you're actually writing up a paper and stuff like that, you're definitely going to want to move more towards matplotlib for making those publication quality plots. But when you're first exploring the data, I highly recommend looking at HVplot here, which is going to allow you to plot your data more interactively. So here I'm grabbing the first 5,000 meters. I'm specifying that I want time along the x-axis, y along the, or range along the y-axis. You can specify your color map here, and rasterize here is basically gonna allow you to work with it a little bit faster, and it'll only load in the data that you want it to. So this gives you a really nice view of the temperature data. It's interactive. And again, this is one line. So you take your data array .hv plot, you tell it what your dimensions are, and boom, you have an interactive plot that then you can zoom into if you want to, say, look at this time range here, and you can go ahead and look at some of the vertical profile there. Just really nice. So another data variable within here is our reflectivity. So let's go ahead and take a look at an interactive plot of reflectivity, which we get here. So again, this is a time height. So we see our nice reflectivity field here. We see this is from that March 14th event. So these are actually snow bands where you're looking at the lowest 5 kilometers of the atmosphere. If you wanted to, say, zoom in on some sort of band here, you could definitely do that and actually look at the fine scale fields here, which is really cool. And again, this is one line. You don't have to go through bokeh. You don't have to go through learning that, all of that. This is a high level, basically just working on the X-ray level, where it takes advantage of those different attributes and able to put this together. So you'll notice that our x-axis isn't super helpful here. This time offset from midnight, that doesn't really tell us much about what time it is. So we add in this date tick formatter. We can go ahead and pass that into the HV plot here. This CLIM is indicating our contour level. So this is saying the color bar starts at -20 and goes up to 40. And now we end up with the nice X label here, where you can see this is going from 0 to 4 UTC on March 14th, 2022. And again, you can zoom in on some of these more fine scale features. So if you want to actually look at this band, for example, you actually go through and look at some of these different reflectivity values. You can look at what time this is from. And as an exploratory analysis, especially for whatever research you're working on, I would highly recommend looking at HV plot. It can make working with this a lot more powerful. So let's look. We also had the mean Doppler velocity within here. So let's go ahead and look at that. In a similar case, we do mean Doppler velocity, grab the lowest 5 kilometers, set up HV plot with time and range, feed in our formatter, and this is the mean Doppler velocity from that same storm. And if we scroll, we can actually look, and you'll see that this is the field is radial mean Doppler velocity, positive for motion away. So basically the red areas are where you'd have your updrafts and that sort of thing. So if you actually wanted to like zoom in on some of these updrafts, you can go ahead and do that and look at some of these fine scale features within the snowstorm. So understanding some of these different tools and understanding some of the APIs here, whether to use .plot or .hv plot, can be super powerful when you're working with your data. The other really cool thing, so here I assign this to a variable velocity plot. I assign this one to a variable reflectivity plot. Now that we have these two plots, you can combine these by adding the plus symbol. So this is going to combine these two plots, and now they're synced. Where, say, for example, we want to zoom into that region, it's going to sync up the reflectivity and velocity plots so you can zoom in on certain regions. And within this notebook, you notice that it's kind of a pain that it's 2 columns. If you pass the .cols 1, that will stack them on top of each other. So if you wanted to look at this case again, you can go ahead and use the zoom here. We can play around and look across all these different times. You want to zoom in, say, on this structure right here. So you can zoom in on some feature. If say you wanted to share this plot with your advisor, you could actually save this to an HTML and have this be an interactive dashboard, or you click the .save button there, and that will download it to your local computer, and boom, you have a plot. So, yeah, I know that was pretty quick, and we sort of went decently quick there, but I hope that provided you overview of sort of why Xarray is so awesome, how you can use it for your sort of data analysis, and also how you can use these interactive plots to really make your exploratory analysis and working with some of these different data sets a little bit more powerful within the Python ecosystem. So I got another 15 minutes or so, so I'll go ahead and get to our last topic here. So go ahead and close this out, discard, and we're going to talk a little bit about intake ESM. I know so far we've been focused on observations, and I just want to take a little bit of time to talk about more model data. So yeah, we'll go ahead and get started here. So has anyone here heard of intake ESM before? So this is new to pretty much everyone. Okay. So intake ESM is a toolkit to work with Earth system model data. It's basically a cataloging tool that allows you to access some of these huge climate simulations. So whether it's the CMAP6 runs, whether it's the CSM large ensemble, CSM2 large ensemble, a lot of these cases where you have millions of data files, you need to make sense and actually just get to working with the data. So we're going to import a few packages here. I'm also going to use Dask here. I'm not going to dig into how Dask works, and this is not a Dask tutorial. We're just going to use it in this case just to allow us to work in a distributed / parallel mindset. I'd highly recommend looking into Dask, but again, I'm not going to cover it in 5 minutes here. So we go ahead and set up our Dask cluster, and let's go ahead and talk about intake ESM. So the traditional workflow for working with Earth system model data is trying to download tens of gigabytes, tens of terabytes, hundreds of terabytes, sometimes even a petabyte of output, which can be a pain. And then you have to look through and find, okay, what's the path to my variable? Like what sort of time ranges are we looking at here? And that sort of thing. So the use case we're going to look at here is the CSM2 Community Earth System Model Large Ensemble version 2. So let's go ahead and look at this. So here, this is FSpec. Basically, this is just a way of looking at a remote file system. So this is calling ls along our bucket. You notice within this file system, we have data separated by component. So we have our atmosphere component. We have our ice. This is our ice model, the land, as well as ocean. And then within each of these, we also have our frequency. So we also have our daily frequency, our hourly frequency, and so on. And then if we go one step further and actually look at these monthly files, you'll see that we have our, these are the actual files themselves. So this is the CSM large ensemble, the 20th century run, and these are the individual variables. So for example, T, which is temperature, U and V, which are wind components, and so on. So if we actually wanted to load this into Xarray, we're going to load that in, and then we get our nice Xarray data set. And so this requires you actually looking into some sort of file system. It requires you knowing exactly where your files are located. And then you have to set up all this logic for, like I was showing before, like where you actually have to know your file path, which can be a pain. So that's where if you wanted to work with multiple variables, you basically, and I'm sure this looks familiar to a lot of your research, is you set up some sort of loop to go through, you loop through different variables, you're combining data sets, and this all is basically boilerplate code across your research. Like you're going through, you're reading in multiple data sets, you're merging, and so much of your time is also spent on just finding these data sets. So this is where intake ESM comes in, is we basically provide these data catalogs. So these data catalogs are essentially pandas data frames that not only contain information about where the files are at, but it also includes information about how to combine these experiments together. So in this case, we're going to use a catalog from the CSM1 large ensemble. So we're going to load in this remote file, and that returns a data catalog. So this data catalog has 56 data sets. So that's basically the data set is the experiment and variable you're looking at, whereas the asset is actually the physical file. So you'll see that we have 56 data sets here. So if we call that DF, you'll see that this is actually what our catalog looks like. So it's a pandas data frame. You'll notice that it has the variable field, it has the long name, component, experiment, frequency, and then it has the path. So instead of you having to go through, look through a file system, find out where in the file system it's set up your own logic for how to set up that string to actually read in the data, this is all provided for you. So if you actually wanted to work with some of this data, so say you wanted to search for, let's say you're doing a research project where you're interested in the temperature, specific humidity Q, as well as temperature and salt. So you'd call .search, you'd feed in your query for your variable or your frequency, and that gives you your catalog subset. And if you wanted to actually load in your data, you'd call toDataSetDict, which is going to load in your data sets. It will read in the data set, merge them together, and then it returns a dictionary data sets where you don't actually have to do the open data set. You don't have to decide on how to merge things together. It all does it for you. Also, the other nice thing it allows you to do is you don't have to think about the path, whether this is located in the cloud, whether it's located on your high performance computing cluster, it doesn't matter. You just have to, the only thing you worry about is reading in some data catalog. So we get this dictionary data sets, which might seem a little weird. So what is this dictionary data sets? So this dictionary data sets is basically aggregated across these different experiments. So you can see it's the atmospheric component. It's from the 20th century run, and this is at the monthly time scale. So let's say we want to look at the RCP 8.5 scenario. This is the most extreme scenario from the CMIP5 experiments. We can go ahead and read in that at the monthly frequency, and we have our data set here, where now we can actually do our analysis and that sort of thing. The other nice thing this allows you to do is be able to write functionality that works at the data set level here, instead of having to work at the individual files. So if we want to look at like the ocean data set, we can do that as well. So this is the ocean data set, which has our salt variable, which one thing to notice here is just how big these data sets are. So that's 1.2 terabytes is how big that data set is. And you're able to, I mean, just take a look at it, see what's in there. And you're not actually loading anything into memory. You only have 10 gigabytes of memory on this, but you're able to at least search, look at, and sort of see what you want to do with the data before you actually apply the computations. And this is where Dask and the general Pangeo space really comes in to help. Because otherwise, I mean, I'm sure most of your computers wouldn't be able to store just a single data set. So that's where the real power comes in. So let's go ahead and write some analysis code. So the 3 steps you usually do to access your data, like I mentioned before, you read in your data catalog, you search for your variables using .search, and then you call toDataSetDict, which is actually going to load in your variables. So let's look at temperature and humidity. So we're going to load in variable T and Q from the atmospheric component. We're going to look at the monthly frequency, and we're interested in the RCP 8.5, which is the future scenario, the most extreme one, and then the 20th century run as well. So we've subsetted our catalog. Now we only have the runs that we're interested in. We could see the start time and end time. So the historical run being 1920 to 2005, and then the future scenarios being 2006 and so on. So we load in our data sets using our toDataSetDict. which now gives us the dictionary data sets. And then we can load in our historical data set. So you'll see here that we have our historical data set, which is 250 gigabytes for each variable, or 500 gigabytes between both of these. Let's say we want to look at some given latitude, which you could plug in whatever latitude and longitude here you wanted to. But we can create a time series here from this data set, which again, like I said, is huge, like 250 gigabytes in this case. So we're going to grab the first member ID. We're going to grab a single vertical level. We're going to grab the first one. And then it's the lowest level. And then we're going to select across our latitude and longitude. And using this method equals nearest, like I mentioned before, is going to allow us to use the nearest neighbor, where it's going to grab the closest point. And then we're just going to look at temperature in this case. So if we run this, again, this is querying 250 gigabytes of data. We get a nice time series here for our temperature at this given location. And if we want to go even further, say we want to go across like a longer time scale, go ahead and run that. It'll take a few seconds to actually look across the full ensemble there. But yeah, you can think about writing these sorts of queries on your data set using the iCell and cell and working with this data set. So I'm just going to stop that. Go ahead and put that back in. Yeah, in the interest of time, I'll keep moving along. So a lot of the time, the sort of workflow that you usually do is write some sort of function to operate on your data set. So say in this case, we want to write a function that reads in some data set and a variable. We're going to select the first member ID. We're going to grab a single vertical level, the closest to the ground. We're going to grab the first 5 years worth of data. Since this is monthly data, we're going to grab the first 5 years. And then grab the nearest to that latitude and longitude. So you run that through our data set, and we end up with 5 years worth of analysis there. We can see the specific humidity for a given location. And then let's say we want to do this across all of our different experiments. You could go ahead and loop through your dictionary of data sets, applying your analysis and visualizing as is going across. And within the RCP85 scenario, you can see this is our time series for a given location at 40 degrees north. Sort of a time series of your temperature, as well as yeah, if you want to plug in specific humidity, you could as well. So this is kind of how you'd work with this dictionary data sets and sort of write your analysis code here. Which again, you're not hard writing the path. You're not worried about the path. You're just worried about operating on the data set itself. One recent development has been this idea of a data tree. So this has been new within the Pangeo community. And basically, instead of a dictionary, where if you actually print that out, it's kind of messy. This basically allows you to work with this hierarchy of X-ray data sets, where it's the idea of these different groups. You can see the atmospheric 20th century run with the monthly data, and it gives you that similar interface of working with X-ray data sets where you can drill into the different coordinates and that sort of thing. If you actually want to look at the different member IDs in here, you can, and that sort of thing. So that's a little bit easier to work with and a little bit cleaner. And then here it's a similar type method. It has those same cell methods. So if you want to look at that given latitude and longitude, grab the nearest point, you can do that directly with the data tree as shown there, and loop through and go ahead and plot your data like that. So this is looping through for both temperature across those different experiments. So I know this is a pretty brief overview of Antique ESM. And I know everyone here might not be working with Earth system model data, but I highly suggest taking a look at this package. We released a new version a couple weeks ago. There's a great tutorial here on working with CMIP6 using the Google CMIP6 catalogs that has about a petabyte of CMIP6 data, where again, you don't have to go through ESGF, you don't have to go through and download tens of terabytes or hundreds of terabytes of climate model data. This is all using cloud, and you can work with these different data sets and create these really nice figures and that sort of thing using this sort of framework for analyzing Earth system model data. We have how to build these sorts of catalogs and that sort of thing, a whole tutorial on building those. So if you wanted to actually say in your research, you were running some CESM, Community Earth System, a fully coupled simulation and wanted to build your own catalogs and not just use the publicly available ones, this shows you how to actually build a catalog for your research. And then probably the page I'd recommend checking out the most on here is under the frequently asked questions. You'll see there's a list of catalogs. So some of these are actually on the MSCAR HPC system. This is Cheyenne/Casper. So there's some catalogs directly on there, but there's also quite a few cloud catalogs where if you're interested in working with, say, the CSM1 large ensemble or the CSM2 large ensemble, we have catalogs available there. So yeah, with that, again, check out the intake ESM documentation. It's a super useful tool to work with these different sorts of Earth system model data, and something definitely worth checking out. So I know I went a couple minutes over. We started a little bit late. I'm glad I was able to at least cover everything, at least somewhat, and I will take any questions. Thank you so much for attending, everyone. Python's awesome. It's really nice. It enables this sort of open source research, open science, and that sort of thing, like I was showing you before, being able to create these open science examples and really sharing your research and sharing some of these different tools is a lot of fun and something I encourage you all to consider doing. Thanks so much. All right, any questions? The materials for this will be available. That site's not going anywhere. So if you want to go back through some of these notebooks, experiment, try different things out, you can always launch that Jupyter Hub again and go through some of these examples. Yeah, thanks so much. And yeah, have a great day. We're good. Oh, I would recommend you shut down your server. So if you go
real quick, like everyone at Zoom, like please join like
Hub
the
control
original
panel.
Zoom.
Stop my server. Thanks so much.